Okay, thank you very much. Can you all hear me? Yes, good. Thank you very much, Roger, for the introduction and the organizers for inviting me to present my project, which we're running since a couple of years in a small scale. Currently, I'm trying to advertise this project to UK astronomers. So this is my 10th talk in the space of a couple of months. There's 17 more to go. The idea of all these talks, and this one seems to be the most important one because in terms of miles traveled per audience member, this is quite effective. So thank you all very much for coming. So HOISCAPS itself, as you've seen on the previous slide, stands for Hunting Outbursting Young Stars with the Center of Astrophysics and Planetary Science. This is the group I'm working in at the University of Kent in Canterbury. What I'm going to do today is I tell you initially a little bit about star formation to explain to you the research we're trying to do. I show you, or I try to explain why I think amateur astronomers can help us with their observations to progress the science and help us to do our research. I'll show you some results, and at the end, how to, in principle, participate in our project. So let's start off with a bit of background. Many of you have probably seen something like that. This is how star formation works. Stars form out of clouds of gas and dust. Initially, these clouds are very massive. We're talking up to several million times the mass of the sun. They're very, very cold, typically only 10 to 20 Kelvin. That is minus 200 and roughly 60 degrees below zero, sorry. Much more comfortable than this room. In these clouds, because they're very massive, eventually in certain places gravity will be the strongest force and starts to push or pull material close to the center of what will become finally the star. So that is the onset of the star formation process. Very quickly, that collapsing object, or around that collapsing object, you form a disk of material which forms due to angular momentum conservation, and it's out of that disk where the material will be moving towards the central object. It's been accreted onto the central object, but these disks are also important because this is where the planets are forming. Right? So the formation of planets, and we've heard a lot about planets in the last talk, is linked inextricably to the formation of the stars themselves. So the mass in those clouds, or those collapsing parts, eventually is dissipated either by the radiation of the central star or by some of those jets which come out. All these accreting young objects, they eject jets along the rotation axis. And eventually you're left over with the central star, or what will be the star, still a young stellar object, that accretion disk around that is still accreting some material, but also at the same time forming the planets. And this is basically what we're trying to understand. One additional slide on these clouds of gas and dust. If you take a picture of them, can we dim the light a little bit to see the images a bit better? That would be nice. So if you take a picture with your telescope and hold the light on the left, what you basically see is, in particular, the dust in these clouds that scatters and absorbs the light. So this scattering process is dimming the light, but it also makes the light redder. The reason for that is the blue light is scattered preferentially, so more of the red light will actually pass through the clouds, And then if you actually look at the infrared, where the wavelengths are even longer than at optical light, you can start seeing the stars shining through the clouds. That process is not just going on in these interstellar clouds, which have these gas and dust grains in. This process also happens in the disks around the young stars. These disks are formed out of that material, and basically the light from the central star could, under certain circumstances, pass through the material in the disk and reaches the observer. And because you have some idea how these dust grains actually scatter and absorb the light, if we investigate how the light changes, in particular how the color changes, we can actually infer something about the composition, or at least the scattering properties of that material that is in the disk. And some of these scattering properties, they actually tell us something about the size distribution, right? If we make the dust grains larger compared to how they originally were, then they will scatter the light in a slightly different way. The color change is going to be different. So in the extreme case, if I make loads of bricks, right, I want to get to planets from my dust that I originally have, so I have to start very quickly making these dust grains very large. So if I have loads of bricks, which are very large, much larger than the wavelengths of the light, then all the light of all wavelengths is simply going to be absorbed by the same amount, and the color will not change, it's just dims. If the dust grains are very small, the light will dim, but also the color will change and the star will appear more red than it is if the light doesn't go through that material. This is something I'll come back to. So what we're interested in is basically how, during the star formation process, do the stars actually gain their mass? Is it just all accreted at a constant rate, or does it change? And how does that evolve over time, and how long does it take? And how do the, I put in brackets, terrestrial planets form? Planets like our Earth. We know, we've heard that in the last talk as well, they form reasonably close to the central star. Things like Jupiter, they form further out where all the gas and dust is. The ice giants form even further out where all the ices are. The terrestrial planets, they form very close. And to actually answer both of these questions, or to make any kind of progress, what we need to do is we need to find out what is the mass accretion history of the stars. So how over time do the stars accrete mass? And linked to that is what is the actual structure and the properties of the material in these accretion disks in the very inner bit. And we have some idea how the mass accretion rate process works. So this is that plot here, which basically, as I sketch, it shows you how the accretion rate, which is the y-axis, should change over time during the star formation process. And what we know is the accretion is typically very quick. It only takes roughly 500,000 years to assemble roughly one solar mass. If you're trying to make the sun, the object in the center gains its final mass, or almost its final mass, within about 500,000 years. And then the remaining part of the accretion process just adds a small fraction of the total mass. And these disks, which supply the rest of the material, they live for up to maybe 10 million years. So you basically have only that window to make the planets in these systems, and hence that process has to be very fast. Remember, you're starting with these tiny dust grains that you have in the interstellar medium. They're about a micrometer in size, typically, and within a very, very short amount of time, they need to stick together and grow to actually form planets. So people try to investigate that. And what we also know is the accretion rate, the black line here, isn't constant. It's highly variable. So typically what you get is you get these outbursts where the accretion rate suddenly increases by several orders of magnitude in some cases. These outbursts compared to the total time scale are quite short. And one example of one of those outbursts is Fu Ori that some of you might have heard of, which used to be a 16th magnitude star, and then the mass accretion rate increased by roughly a factor of 100. The star became brighter by about 5 or 6 magnitudes and has been bright more or less ever since and hasn't gone back. So what we're trying to understand is how often do you get these outbursts, how long do they last, and how strong they are, simply because they have a very, very strong impact on the nearby disks. Because what happens is if you increase the mass accretion rate, you increase the luminosity of the central star. That makes it hotter and also much more luminous. And that radiation interacts with the surrounding accretion disk where you try to form planets. This energy changes a lot. It changes the chemistry. It might evaporate the dust grains, all ices that have somehow formed on these dust grains. So it alters the chemistry and the composition. And if you want to model how planets are forming, what we need to know is, at least statistically, how does the mass accretion rate change over time. And if you want to model that, we also need some observational evidence of the structure in these disks, right? They're not nice and smooth. There might be some structure that causes instabilities that actually causes these outbursts. On the right, there's some pictures of some of these disks. This is Fu Ori, so it's similar to the picture that we've shown before. The central star is blacked out, and then I think this is a Subaru image. You see the structure of the disk. It's not nice and smooth, and there's a scale which you can't read, but what that bar roughly is, it's 400 astronomical units. So the solar system fits roughly into the inner part of these pictures. But that is not the inner accretion disk, right? This is the whole accretion disk that is very far out. So the problem is, of course, resolution. Can you do better? You can use or spend, I don't know, $5 billion, build the Hubble Space Telescope, and then you get images like that, where again you have a young star in the middle that is hidden. You have the accretion disk, which is edge on, so you see reflected light from the central star on the surface of the accretion disks. These disks are not flat, they're not like Saturn's rings, they're flared. They get wider if you go further away, and you have the jet coming out. Again, you can look at the scale bar, that's 200 astronomical units. So in terms of resolution, the best you can do for the nearest young star, so we can see those disks with Hubble, is about 35 astronomical units. In terms of trying to resolve these disks, I wouldn't call that resolution. So you can't really see anywhere into the center. If you spend a little bit less money, 1 billion euros, you can build ALMA in Chile, and then you can do things like that. You can take a radio interferometry image of one of those disks. This is HL tau, where you can actually see some nice structure. There's rings, there's gaps of material, so you see there's clearly some structure going on. And then you can look what is the resolution in these pictures. 5 astronomical units. For the nearest stars, most stars are further away than HL tau, but for the nearest ones, we can resolve 5 astronomical units. So anything between us or the Sun and Jupiter. Then you can use the SPHERE instrument at the VLT, and you can take some nice infrared images of disks. Look pretty much like the ones from Hubble. You get these absorption features where the light doesn't come through, the star is blacked out. There's another nice one over there, and again you see there's some structure, and the resolution is roughly like what you get with ALMA. Many of you have probably seen that picture. Again, an image of a disk, PDS 70. Again, a very nearby star, and out pops a planet. But this is, in terms of resolution, you can't really get better than 5 astronomical units, right? If you want to look at the very inner bit of these disks, we can't do that with direct imaging or interferometry at the moment, and probably also not in the foreseeable future. If you want to go significantly below 1 astronomical unit in resolution. What we are trying to do is, and this is an artist impression of one of those disks and young stars in the middle, is using an indirect method. So this is how a disk might look like. You might have some structures in this disk. Remember, all that material is rotating around or orbiting around the central object. And every now and again, one of those structures might just cross the face of the star and absorb or scatter some of the light. And if you monitor the brightness of these young stars over time, then you might see these things. So you might see a dip in the light curve, and when that structure has moved further away, then the star returns to its original brightness, and if you wait long enough over one period and that structure hasn't changed in shape, it will come back, and then you can actually measure how far away from the central star it is, because you know the orbital period, you use Kepler's laws. Guessing the mass of the spectrum of the central star, you can then work out the radial distance. You then know how fast it is moving. So if this was the sun, this would be the place where the Earth is. You know the Earth moves with 30 kilometers a second, so you know exactly how fast that material is traveling. Hence, from the duration of that dip in the light curve, you can work out the actual scale of the feature that has blocked the light. And this is a really nice technique, and every talk isn't good unless you have an actual prop. So I'm going to show you how that actually works. So in principle, that is my star. I'm going to observe that, and I made an artificial disk, which is basically just a transparency with slightly colored slices. And basically, if I move that across, like the material in the disk, you can see the colors change over time, right? And if I'd actually tell you with what speed I'm moving that transparency across, then you can work out how big these slices are. And you might say, oh yes, I'm sitting here, I can see that, they're about 1 centimeter or something like that. But you can observe this light quite far away, right? So the actual resolution that you can get is very, very high. In principle, the limiting resolution is the size of your central star. Because once the material moves exactly the distance as that is equal to the size of the star, another amount of material is in front of it, and you can study the next bit of material and its property. So in terms of resolution, that's quite an improvement, and I always do this with a car, because that's what most people know. So the resolution of your eyes, just to get you started, is about 1 arc-minute on the sky, and that means with your naked eye, you can see that the car has 2 lights if I park that about 5 kilometers away, roughly, if it's not behind a tree. With the best ground-based telescopes, without any adaptive optics, if you're lucky and the seeing is really good, you get about ½ arc-second resolution. That corresponds to the car being parked 600 kilometers away. So basically, somewhere distance from London to Edinburgh. ALMA, with the radio interferometry, the resolution can be pushed down to 0.025 arc-seconds. That means parking the car on the other side of the planet. So in terms of the nearest young stars, that is that Sun-Jupiter distance, these 5 astronomical units. You can't do any better with any instrumentation that we have. With our technique, if you do that, the resolution is about the size of the star. That's 1% of the astronomical unit. And that means I can park my car on Mars and still see there's 2 lights. Right? That's how that in principle works. And this distance is basically calculated for the typical distance of the stars we monitor in our project, about 3,000 light years away. Right? So that is basically what we do, and this is where that project comes in. What we are trying to do in HOISCAPS is basically long-term, high-cadence, once a day, multi-wavelength optical monitoring of young nearby star clusters and star-forming regions with smaller intermediate-sized telescopes. smaller intermediate sized, anything from 10 centimeters to whatever is available. And when I started that project, I was mainly jealous of the instrumentation that the amateur astronomers have, or some of you actually have in their back garden. So we use that telescope that sits in Kent, and that's a 40 centimeter. And why do I think this will work? So as I said, we're trying to monitor roughly once a day, and that roughly corresponds to the best resolution we will have. So in one day, the Earth roughly moves 2 solar diameters in distance. Because the young stars are bigger than the Sun, about 2 to 3 times the solar radius, that is basically as often as we need to image one of those stars to get the best resolution possible. Why does it work? On the left is a typical radar image of the UK, not from the last couple of weeks. It's terrible. There's no clouds. But in a typical radar image, this is where our observatory is, and what you know is it's typically cloudy in the place where you are when you try to do observations. We all know that. But if you pick out a random satellite image of the UK, there's always a not tiny fraction of the UK where it is actually not cloudy. In this case, Wales and Cornwall, which is weird. So typically, I think I looked at quite a large number of those. In 90% of the cases, there's one part of the UK where it is not cloudy every night. You just need to move your telescope there without driving it around. So I made a list of all the amateur societies that I could find in the UK, all the red dots. You see them mainly in the places where people live, so there's nothing in Wales and nothing in Scotland, where the observation conditions are probably at least the darkest. But each of these societies probably and typically has about 50 members. There's at least 2 or 3 in each of them who have a nice telescope and do imaging. So this is why I'm trying to engage as many of you to participate in this project. And I think it will actually work. So what have we done so far? This is basically our target list and the number of images that we have obtained so far in the last 3 years for the project. I still have to say a large fraction of that is still coming from the observatory at Canterbury, but about 10% of these data points are from amateurs like Watcher and others who've been there from the start. One thing, there's loads of targets that everybody takes pictures from anyway or has in the past, right? The Orion Nebula, the Elephant Trunk Nebula, the Rosette Nebula, and all these famous nearby star-forming regions where people take images anyway. So they are amongst the target regions that we have picked. This is an example of one of the data sets we have from the amateurs, from Mark Shelley, from Ashford. This is just 3 images blinking that he took over about a month. And what you see immediately, there's a lot of stars that vary. There's that one that disappears completely in one of the pictures. And there's a couple of others. I drew the circle around the 10 most obvious ones. And these are the ones you can see with the naked eye. So if you let the computer actually do this, a large fraction of these stars varies. And you can see these young stars, and this is NGC 2064, that's near the Christmas tree cluster. There's quite a lot of variability going on, especially on a level that you can't do with the naked eye, but with the computer. I'll show you some of the example light curves that we have. This is NGC 7129. That's the brilliant target. That's the only target we have that you can see every day of the year when it is clear, because it never goes below 30 degrees above the horizon in the UK. And there's a star called B3350 Ceph, which is this one on the top. And I'll show you the data. This is our light curves on the x-axis, the number of days, either Julian dates or days since we started the project. And on the y-axis, simply the magnitude. And that star doesn't do really a lot, but almost at the beginning of that project, it had one of those dips where material moved in front of the star, dimmed the light for about a month, and the dimming was about 2 magnitudes in depth, more or less the same in all the filters, and then has recovered and it's been bright ever since. Ignore the points above here. This is hydrogen alpha line. The only thing that it shows you is that this is actually a young star that is accreting, so these are not red filter data points. On the right, I've basically plotted the color versus the brightness of the star, and the green line here, this is just a fit to the data. The orange and the blue is a prediction from the model. If this was normal interstellar dust, how should the brightness change with color? And you see that kind of works pretty well, but only for the first bit of that eclipse. For the second half, it doesn't work anymore. So the material that makes the deep part of the eclipse is different. It's either completely opaque or something changes in the size distribution, or at least the scattering properties of that material. So what you can then basically do, you can play around with some numbers. If the star is a quarter of the solar mass, that material was at 1 AU. That's a pure guess. You have to guess something. The duration was about 2 months. Then you can work out from the depth of that how much mass was in that, assuming the structure was a sphere. Again, that's an assumption. And you find it's 0.1% of the mass of the Earth. You need that amount of material to make this kind of effect. A second example in the Pelican Nebula. So W14-19-1 SIG. That's this one. That's our data set. Again, what you see here is there's multiple dips. There's one here, there's one there, there's one here, and there's one there. Again, in terms of the behavior, how the color changes with brightness, this is steeper than what you expect from normal interstellar dust. So the dust grains are probably larger than normal. So that's what we actually expect. You start to make these dust grains stick together, make them bigger, because at the end of all that, you want planets out, right? Again, here we can almost guess the period. If there was another eclipse here, it would be a clear 180-day period, because these two are 180 days apart. These two are 180 days apart. The gap here is exactly twice 180 days, so I'm not sure yet what's going on. Either the structure was slightly misaligned during that, or it's actually a double structure and it's come back, and then we have to wait another year and a half and see if there's any periodicity. But again, if you do this, you can work out this is about 1% of the mass of the moon with some sensible assumptions. So a student of mine, master student, she's actually gone through all the light curves and really started to do some statistics, right? So we have the distribution of how deep are these eclipses in terms of magnitude in the visual. So there's lots of shallow ones, you might have guessed that, and then, but it's a nice kind of power law. There's less deep ones, and the same is true for the duration of these dips. And one question, of course, is, can we actually detect all of them? Or do we miss some of them because there's bad weather, there's gaps in the data, and so forth? So we started to simulate that. Another student has started to do this. So basically, you say, I have a distribution here. This is the number of these dips or the frequency. And this is the magnitude. So 1 magnitude dips are here. These are half a magnitude dips. And the red line basically tells you this is what we give in. The computer simulates the whole process, makes simulated light curves, and so forth, and tries to mimic our survey. And in blue is the number of dips that you get out if the noise in your photometry is 3%. And you see the curves roughly agree. If you have a bad telescope or the star is very faint, your noise is, let's say, 3 times higher. And then what you find is you put the same red distribution in. What you get out looks slightly different. So you seem to find more objects of about less than half a magnitude of depth in the dip. And this is simply noise. So we know if you have any detections, what we need to do is, if you want to do statistics, we need to correct basically for these effects. But it's just the start of these simulations. And hopefully very soon we can do that a bit better. Then you find all sorts of other things. That's another of our light curve, where the star is basically more or less constant, and then every now and again it pops down like a little dip. again, looked very strange, and so we thought, okay, maybe what's going on? And it turns out if you fold the light curve with the correct period, then it turns out this is actually a noise eclipsing binary, and the period 0.588 days. I think the actual period is twice that because the depth of that looks like two stars, roughly the same magnitude, eclipsing each other more or less totally. So I think the period is about twice that, or exactly twice that. But this is one of the things that you find in these data sets. And one other thing I discovered, because I have a student, an A-level student coming next Monday, who actually will be tasked to actually find all these periodic objects. So when I tested the software, I found this one, where the period, you see the light curve looks completely noisy, just going up and down randomly over these 800 days of data. But if you actually try to fit the period, you find it's 16 hours and 9 minutes. And because we get data sets at 3 wavelengths, I thought, oh, we independently measure the period for each of the 3 data sets. And they agree within roughly 1 second of each other. That's actually not too bad. So you can do quite interesting things. I was surprised. With hindsight, I shouldn't have been, because each of the measurements we do is basically integrate for 1 hour. Each of these data points is a 1 hour measurement of the brightness of the star. We've done this over several years, and because the period is so short, you have a large number of periods. And hence you can measure these periods extremely accurately for these objects. But how to actually participate? Well, if you're interested in helping us in that science, we have a website, and I can actually click on that, where all the instructions are there. So you can read the instructions again for the observations. It basically tells you there's a target list. Please observe these targets in any field you like, any field of view, anything you want. That's completely up to you. At the moment, we're not really coordinating that. The target list is basically here when you scroll to the bottom. There's lists, there's targets for the winter, and then there's targets for the summer, and then there's some special ones which we every now and again pop in. So you can do that. We also, if you click here, we have a Facebook group which we like to use for discussions. So if you want to stay informed about that, you just become a member of that group. And the only thing that we require you to do is you do some basic flat fielding and dark corrections for the data. If you don't flat field the data, basically the calibration of the brightness will be much more noisy. We estimate probably a factor of 3 or 4 worse than what we do with a flat fielded image. That is one thing. And finally, if you take several images for one filter per target in a single night, please add them all up and do not submit the individual ones, because we're interested in the long-term behavior. So we try not to collect more than 1 data point per instrument per night for a particular star. Once you've done your observations, all you need to do is submit that picture, that FITS file that you've made to our server, where all you need is a login, and I think that works as well if I do that. So you can submit images by just clicking on upload, and you literally drag and drop your images into that little box. You upload them, and then there's a little processing to do, which I can show you very briefly. Basically, it will list all the images that you've uploaded. I've done this before, and there's 4 simple steps. So one, basically, you need to tell us for what target that observation has been done. So this is Lambda Ori, so we're trying to find that somewhere. Where is it? There. And then here, it asks what device. So when you log in the first time, it will ask you which CCD do you have. So we have 2 different sets of images. So this has been taken with the Beacon Observatory. So you just click on that, say OK. Then you're done with the first step. Then there's a second step where the software will basically automatically pull out all the rest of the information out of the FITS header, in particular the filter, the exposure time, and the date and time of the observations. When you do this the first time, you simply train the server and tell the server, in my data, which FITS header corresponds to which of these three informations, and it basically displays it on the screen, and all you do is you check it actually has found it correctly, and you accept that. And then we have all that into the database. And then all you need to do is calibrate the coordinate system, the astrometry, and the magnitudes. So for the astrometry, we basically use astrometry.net. I've done this before. That usually takes a couple of seconds. And what it just does is it basically draws red circles, if you zoom in, around the stars where they should be, and if there's basically red circles on stars, then it has done that correctly without any problems. So that usually works fine, and then you can accept that. And the last step is really to do the photometry, where basically the software will go detect all the stars in the picture. Oops. And tries to calibrate that, and the bottom graph basically shows you this is our calibrated magnitude against the difference of the magnitudes in your image and the calibration catalog, right? So that should be 0, that is fine. The green line tells you the typical scattered, which also tells you how accurate the photometry is. So for the bright stars here, that's a handful of % at most. For the faint stars, of course, that goes up. Once you're done with this, you press the green button, and that will submit all the photometry of every single star into our database. So this is the difference of this project compared to AAVSO, for example. We have the photometry of every star in the picture, so typically 10,000 sources in a typical image. So that's all you need to do to actually process the images, and then you can actually access the data. So the data, as soon as it is in the database, is freely accessible. We have, and it's the last thing I'm going to do, this kind of light curve plotter, which you actually can access without having a login. So that's freely available. It says experimental because we're still trying to improve the usability, so that it's not nice at the moment. That will change in the next couple of weeks. But you can just type in a coordinate here, just picking a star that I've tried before. This is a live query, so luckily we have internet here, and it will basically make a list of all the stars that are near the coordinates. You click on one, and then it will basically plot the light curve for you in a couple of seconds. So these are all it's color coded, and you can play around with this. You can switch on error bars if you want. You update that, takes a second or two, and then it will overplot the error bars that we measured during the calibration process. You can't see them, but you can basically zoom in, and then you can see the size of the error bars compared to the variation of this source. And there's a button here on the bottom left where you can actually download the data. So if you are interested in that particular star in that field, if you download that, it gives you a basic text file which you can dump in anywhere. So if I open that, just for the fun of it, it's a lot of numbers, but there's a lot of data points in the graph, and there's basically on the top it says you what column is. So that's just an ID number, magnitudes and errors and different filters and so forth. So you can play around with that if you like. So, and after that, what happens is we actually write some papers. We've written some of them already, one in 2017, where the amateurs decided we don't really want to be on the offer list. We don't think we did enough. But for the paper that we've just got published last week, you will see the last two lines are amateur astronomers who participated and helped out with the data. So Roger is here, he's chairing the session. Is anyone else in the room? No? Okay. I always would like to meet those people because I managed to meet now 3 or 4 of them who actually participated. And in September, I have a new PhD student who will solely work on data for that project and investigate all the science and more that I have explained. So I think my time is up. So here's the web addresses. Again, the simplest is Googling Hoist Cups instead of writing these things down. We have that Facebook group. And what I forgot, we have that YouTube channel. So if you go back to these, to any of these websites here, there's a Get Help button, which basically gives you a video that you can click that are also accessible on YouTube. And you can just play those. And it actually tells you how all these steps are done. So the full video, there's one that explains the whole process from the beginning to the end. It takes about 45 minutes. So you can watch them for each of the separate sections. And that is the last thing I want to mention. So thank you very much.